Question 15, 2011, Higher Paper 1. 3 points in space, S, T, U, were given their coordinates, told their collinear. We've to calculate the ratio in which T divides S, U. Now, I'm going to show you how to do this using two different methods. First method, standard method. It may seem a lot more complicated, but it's very powerful and it involves an extremely useful technique, position vectors. Second method will visit the points in three-dimensional space, have a wee look at them, and then use what appears to be a much simpler thinking out method using the coordinates. So first of all, position vectors. We need to first establish what a position vector is. If we're in space with, say, a couple of points A and B, and we know their coordinates, say this one's 1, 2, 3, and this one's 4, 7, 9, and we're interested in the journey we have to make from A to B. So A to B, travelling from A to B. Somewhere there is an origin. The journey we take from the origin out to the point A is called the position vector of point A, and it's denoted by lowercase a with a little line under it. The components of that journey, what must you do to get from the origin to the point that has coordinates 1, 2, 3? You have to travel 1 along the x-axis, 2 parallel to the y-axis, 3 up parallel to the z-axis to get the instructions for your journey. So these are the components of the position vector A of the point A, which has coordinates 1, 2, 3. So the components are just the same as the coordinates of the point. Similarly, travelling from the origin up to the point B, position vector B will have components 4, 7, 9. These are the instructions for travelling from the origin up to the point B. So, travelling from A to B, let's go an alternative route. Let's go from A to O. Ouch, that arrow hurt. That means you're going against the arrow, you have to have a negative there. So we have a negative A followed by a B. So let's do that again. A to B minus A plus B. Doesn't matter the order you do this in, we could swap that order around, have a B followed by a minus A. All we're doing is doing a B journey, same distance, parallel to this, minus A would come down there, same distance as this, parallel to that. That's minus A. Remember, going from there to there, ouch, we went against the arrow, that hurt, so we stick a minus in there. But there's the correct way the arrow should be to get from A to B, B minus A. So that's B minus A. So there is the very general result, and this works for any pair of points. Travelling from A to B, position vector of B, that's where you ended up, your destination, minus position vector of A, that's where you started. So A to B is position vector B minus position vector A. We then fill in components. We know to get to point B from the origin, position vector B has components 4, 7, 9. To get from the origin to A, position vector 1, 2, 3 for the components. Doing a subtraction, 4 minus 1 is 3, 7 minus 2 is 5, and 9 minus 3 is 6. So we subtract the x components, subtract the y components, subtract the z components, and we now have the journey from A to B. It's 3, 5, 6. So that's your basic result for position vectors. It works for any pair of points, as I said. If we're travelling from P to Q, position vector of Q minus position vector of P. If we're travelling from S to T, st, it would be position vector of t minus position vector of s. So let's tackle this question using these position vectors. So let me just clear out what we've got there, and let's go back. So let's find out what on earth we're doing when we travel from the point S to the point T. So the journey from S to T in terms of position vectors would be T, that's your destination, position vector of T minus position vector of S. That's your starting point. We know the position vector of T. It's the same components as the coordinates of the point. So it's minus 16, minus 4, 16. So that's position vector of T minus position vector of S minus 4, 5, 1. That'll be the components of S. And it's now just a wee bit of arithmetic to do the resulting component. Minus 16 minus minus 4, that's minus 16 plus 4 is minus 12. Minus 4 minus 5 is minus 9. 16 minus 1 is 15. And for reasons that you'll see in a wee minute, we're going to write this. You notice that there's a factor of 3 in all of these. So let's take that factor out and say that this journey of minus 12, minus 9, 15 is 3 times a journey minus 4, minus 3, 5. So 3 times this journey would give you this journey. Let's do the same for the journey from T to U. So travelling from T to U, position vector of U minus position vector of T. We know the position vector of U, minus 24, minus 10, 26. Minus, we know the position vector of T, minus 16, minus 4, 16. A little bit of calculation. Minus 24 minus minus 16, that's minus 24 plus 16, that'll be 8. Sorry, minus 8. Minus 10 minus minus 4 is the same as minus 10 plus 4, be minus 6. And 26 minus 16 is 10. Now, finding common factor in all these, there's a factor of 2. So this journey, minus 8, minus 6, 10, will be twice the journey minus 4, minus 3, 5. And here's an interesting thing. The journey from S to T, let me just show you this journey from some angle in space. It will look like this. So the journey from S to T is 3 times some basic journey. So we can divide this up into 3 pieces. 3 lots of this basic journey. Then travelling from T to U, we continue, and it's twice the same basic journey. So this journey can be divided up into 3 bits. This journey can be divided up into 2 bits. So the ratio in which T divides SU, the order is important here. The ratio that T divides SU is 3 to 2. So the ratio is 3 to 2. And if we look at the answers, this would be choice B. So there's the good old powerful method of using position vectors to solve this problem. However, that's not the end of the story. And what we're going to do next is we're going to visit these points in space, and I'll show you a much easier method of doing this problem to get the same ratio 3 to 2. So here we are in three-dimensional space. Let me just move around a wee bit, give you a feel for this. Red axis, this is the x-axis. Green axis is the y-axis, and the blue axis is the z-axis. So we are in space, there's a horizon in the distance, and we've plotted the 3 points. Just see, there's S, there's T, and there's U. And if we spin round, you can see that they're collinear, they all lie in the same straight line. So what I'm going to do is give you a feel for a much simpler method for doing this question. If I line up, what I'm going to do is look at the x coordinates. So the x-axis just lying along this line here. So if I line up these points, so we're looking at them from this perspective, the x coordinate here is -4. The x coordinate here is -16. And the x coordinate here is -24. So I'm looking at these 3 points sideways so that we can see how they're placed along the x-axis. The distance from -4 to 16 is 12. The distance from -16 to -24 is 8. The ratio involved, T dividing S, U, this dividing this, is 12 to 8. So we immediately get a ratio out of this. We divide both of these by 4, we'll get 3 to 2, which is the answer we were after. So this is using the x coordinates. We quickly get the ratio 3 to 2. Let's do a slightly different one. Let's clear that. And let's look at the y coordinates. Now that's the y-axis, the green axis. So let me just get our perspective sideways along the y-axis. So the y coordinate of S is 5. The y coordinate of T is -4. The y coordinate of U is -10. So this distance along the y-axis will be 9, and this distance from -4 to -10, that distance, not bothered about negatives here, this distance is 6. So the ratio in which T divides SU will be 9 to 6. 9 to 6. Divide both by 3, 3 to 2. And again that ratio appears. One last look at this. Let's use the Z components. That's the height that these 3 points lie above this XY plane. So let's go back to this viewpoint. The height of point S is 1. The height of point T is 16. So this is 1. This is 16. And the height of the point U is 26. This distance is 15. This distance is 10. The ratio in which T divides SU is 15 to 10. Divide by 5, 3 to 2, yet again.